Sometimes you might encounter missing data or non-random sampling. Suppose you want to create a variable as the sum of the parent's education. For each individual I, parent education is the total number of years of education of their parents, mom education is the number of years of education of their mother, and dad education is the number of years of education of their father. The variable parent education will only be valid if you can observe both parents' education. If either is missing, you can't create the variable. Suppose you want to model how a person's education level is related to the total education level of their parents. Child education is number of years of education that a person has completed. If the data for some observations of parent education is missing, the default approach in statistics software is to drop those observations. This method is called complete case analysis, where only the data for which both the outcome and explanatory variables are available are used. Note that you can still use all the observations by adjusting the model. Suppose a variable xk in a multiple regression model has missing data. In this case, you'd use two variables in place of xk. One variable zk is equal to xk when the data is available and 0 otherwise. The other variable mk is equal to 1 when the data for xk is missing and 0 otherwise. Omitting mk can introduce bias because that's equivalent to assuming that xk is equal to 0 where the data is missing. The estimates from this model are unbiased but less robust than those from complete cases analysis. However, you can't use this approach if data is missing for y. If the data is missing completely at random, m-car, meaning it's missing for reasons unrelated to any observed or unobserved factors, complete case analysis won't introduce bias. This is because when we estimate a regression, we aim to estimate the coefficients for the entire population. Since we can't observe the entire population, we rely on a sample. As long as our sample is random, it represents the population, and the estimates are unbiased. When the data is missing completely at random, the randomness of the sample is preserved, ensuring there's no bias. However, this scenario is highly idealized and unlikely to occur in practice. Now let's consider a more realistic situation. We can view missing data as a specific case of sample selection. If sample selection depends on one or more of the x variables, there's no issue because the regression already controls for these variables. Under assumption 4-0 conditional mean, the explanatory variables are uncorrelated with the error term. Therefore, if sample selection is based on the explanatory variables, and these variables are uncorrelated with the error, this constitutes exogenous sample selection or missing at random, MAR, and it doesn't pose a problem. However, sample selection becomes problematic if it's based on y or is correlated with the error term. This is known as endogenous sample selection. Let's explore examples of each case to understand why this is problematic. Suppose we're interested in the propensity of people to save their income. For each individual I, saving is the percentage of their income saved each year, income is their annual income in dollars, age is their age in years, household is the number of people in their household, and epsilon is the error. What if we focus on older individuals and oversample those aged 40 and above, since we think younger people might not be earning an income? Keep in mind that working adults are typically those over 18 years old. This definitely creates a non-random sample of all adults. The missing units systematically differ from the observed units, and the data won't be representative of population subgroups. Although this is not ideal because we're not using the entire sample, we can still obtain unbiased and consistent estimates of the parameters. The reason OLS is unbiased and consistent is that y is conditioned on the x variables and we assume the model holds for all subsets of the population defined by these x variables. We only require that the expectation of savings to be the same for each subgroup of the population as defined by different combinations of income, age, and household size. This holds true only if the X variables are completely exogenous to the errors. If the sampling is based on a completely exogenous variable, we can say this is an exogenous sample. As long as there's enough variation within the subpopulation for analysis, sample selection based on the X variables is not problematic. If this condition isn't met, the issue is with the model, not the sampling process. Suppose we're interested in studying how wealth is related to education, age, and work experience. For each individual I, wealth is their net worth in dollars, education is their number of years of education, age is their age in years, experience is their number of years of work experience, and epsilon is the error. Suppose your survey can only reach people with less than $250,000 in wealth. The super rich don't want to talk to you. This poses a problem because we're interested in whether Y, conditional on the X variables, is consistent across the sample. However, the expectation of wealth across the entire sample will definitely not be equal to the expectation of wealth within a sample limited to those with less than $250,000. If the sample selection is based on Y or an endogenous variable, then the estimator will be biased and inconsistent. Another classic example of endogenous sample selection is modeling income based on education. For each individual I, income is their annual salary in dollars, education is their number of years of education, and epsilon is the error. James Heckman received the Nobel Prize for his work on this problem. We only observe income if the individual is working. If they're not working and accept a job offer, we can observe their income once they take the job. Therefore, the income we observe is from offers that individuals have accepted. However, if a person receives an offer but rejects it, we don't observe their income level. This sampling is based on whether you decide to work, but your decision to work depends on the income you're offered. The higher the offer, the more likely that you are to accept it and be included in the sample. This creates a problem because the sampling is based on an endogenous variable. Let's look at this graph to distinguish between endogenous and exogenous sampling. We plot years of education along the x-axis and income along the y-axis. The errors are normally distributed, so the data is randomly scattered around the regression line. If we exclude observations where x is less than 5, this constitutes exogenous sampling because it's based on x. We assume that the relationship in the subsample where x is less than 5 is the same as in the subsample where x is greater than 5 and as in the entire sample. The fitted line is the same, so it's the same unbiased and consistent estimator. It's just applied to a smaller sample. In contrast, if we drop all the observations where y is less than $10,000, the fitted line shifts upward. In this subsample, the expected value of the error is not equal to 0 but is greater than 0, violating assumption 4-0 conditional mean. This results in biased estimators because the expectation of y conditional on x is not the same as the expectation of y conditional on x, and y being greater than $10,000. For more lessons on econometrics, visit alphas&betas.org.